the area between two curves. In this video, I'm going to show how to use the integral to find the area between two curves. And if you recall, the integral itself is defined as this here, where you got the a to b, and then f of x dx. And one of the interpretations of it is that it can be used to find the area under that f of x curve. So if we go ahead and just draw out some f of x curve here, put in a couple of vertical lines to define the region between the a and the b. And what you do with this is, the integral, you got to remember, it's an infinite sum. That's what that elongated S symbol in the front there between the a and the b actually represents, infinite sum. So you're summing up an infinite amount of things, and to find the area, what you're summing up is an infinite amount of rectangle areas. I'm going to draw this one a little bigger than what you would really have, just so I can illustrate some things. But what you got going on in this representative rectangle is that the height is represented by the f of x, and then this width is actually the change in x, the dx, down below. And you would technically pack in an infinite amount of these. They would get infinitely narrow. The dx would essentially be almost zero. So you got an infinite amount of these rectangles packed in here, so you don't have any gaps between the height of the rectangle and the curve in certain places like we do here. But the idea is that you're just summing up an infinite amount of rectangular areas. So one way that you can think of this concept of finding the area is that it's really like finding the area between the function and the x-axis. And if you think of the x-axis as being y equals 0, which is another way to represent it, then what you could really say here is, okay, I'm going a to b, and I've got the f of x up top, marking the top of the rectangle, and then I've got the y equals 0 down below, marking the bottom of the rectangle, and the height of the rectangle would then be the difference between those two values, the f of x value and the 0 value. If you subtract those, you would actually get the height of the rectangle. So I'm just going to kind of write this as f of x minus 0, y equals 0 being that x-axis, and then dx. So you don't really need to write it like this because minus 0 is just going to go away. But I want to illustrate that you really do technically have two functions going on here to help you find the height of that rectangle. So what we're going to do then is we're just going to change the x-axis, the y equals 0 part, to a second function. So let's see what we get here. So you still have maybe the f of x looking something like this. And then the g of x, let's do maybe the g of x, something like this. A second function beneath the f of x. And we'll still go between the a and the b. And we still need to find the height of the rectangles. We still need a representation for the height of those rectangles that are going to be packed in between the a and the b. But now, the rectangle, if I draw in a representative rectangle, and I'm, again, kind of looking at the area now between an f of x and a g of x in this case. So, in this little region here, I want to find the area between these two curves. And the rectangle then still has a thickness of dx. That's not going to change. But what is changing is the height of the rectangle. How am I going to get that height? Well, it's still similar to what I did up above when I was just basing it off the x-axis. I have an upper function, this f of x. I've got a lower function, the g of x now, instead of the y equals 0 line. And I can still just subtract the upper function minus the lower function. And the difference in those two y values would give me the height of the rectangle right here, this desired height. So in order to get that height, we just need to subtract the two functions. So we would get the integral a to b of f of x being the upper minus the g of x being the lower. You want to make sure and get a positive height. So we always take the higher function, the more, the bigger y value, and you subtract away the smaller y value. So in this case, the f of x always produces the bigger ones, g of x produces the smaller ones. So you do the order f of x minus g of x to get positive heights. So now, for example, let's go ahead and find the area between the x squared and x plus 2 curves in the interval -1 to 1. And what I recommend you do is sketch out these curves, because sometimes it's not clear, which one's the upper one, which one's the lower one. It's easier to see this in a picture. So just draw a quick picture here. Got the x squared, the x plus 2, cross about there. And we'll do this way. So something like this, going up like so. So we got 2 there where the line crosses, and -1 here. At -1, both functions will actually give you a y value of 1. So not the scale, but close here. So -1 actually cross there. And then over here at +1, we just have this little vertical line here. I just want to make sure I see everything I need to see. So the area that I'm interested in is right here. And in this case then, you can see that the x plus 2, the line is actually above the x squared in the entirety of that region, -1 to 1. So that means that even though I got an f of x and g of x, it's going to be a different order than what I wrote up above. And this is okay. You just got to make sure that you're subtracting in the right order. So in this case, what we're going to do is we're going to go from -1 to 1. The x plus 2 is actually the biggest function here. And then we're going to subtract away the x squared. Now, I just get in the habit of writing these functions in parentheses in case I'm subtracting in a different order. I want to make sure I distribute that negative sign properly. And then we will get the dx still out back. And then you can, in this case, just drop off the parentheses. There's nothing really to distribute of note. The second thing is just minus the x squared, dx. And then you can go ahead and complete the solution. And when you work this out step by step, you end up getting this 10/3 as the area between those two curves. So let's take a look then at something else that may happen. Oops, I'll go back one there, sorry. So what about when the curves change from, let's say, maybe you started out with f of x greater than g of x, and then you've got a part where the g of x is actually above the f of x in the desired interval. So maybe something like this, where you've got your f of x, and then the g of x, let's just use something basic here, where maybe it goes like that. So there's your g of x. And maybe we're still going from like a to b. But now, here, the f of x was above the g of x up to this little point. I'm going to go ahead and call that c. And then after c and up to b, the g of x is actually bigger than the f of x. So what we have to be careful of here is that if I switch the order of subtraction, I will start getting different values of the heights. Or I can, think about it a different way. On this side, on the left side between a and c, f of x minus g of x will give me positive heights. But if I keep that f of x minus g of x between c and b, I'm going to get negative heights because the f of x is a smaller value, taking away that bigger g of x value. So what you need to do is you need to find the intersection, in this case the c, where that switch happens between, f of x being bigger to g of x being bigger. And then you're going to have to use multiple integrals in this case to ensure positive results. You want to get that positive area. So basically all you do here is you say, okay, for a to c, we'll do the f of x minus g of x dx. And then we're going to add to that the c to b integral, where we're going g of x now minus the f of x. We're going to switch that order of subtraction in order to ensure that we get positive heights in that second part of the interval. So, for example, here we can look at our two things we were looking at before, the x squared, the x plus 2. But now we're going to go from -1 to 4. So I'm still going to draw in a little representative sketch here, see what's going on. Put the 2 here, get this thing going like so. And this might be I might need a little bit more room for the picture. Actually, I'm going to go ahead and back that up now just to give myself more room. And let's do something like that. There we go. That'll be a little better. So I know the curve crosses at -1. It gives me a 1 for both there. And then I need to find where these cross over here. Is it 4? Or is it something different? And the way that you find where it crosses is just set them equal to each other. So x squared will equal x plus 2. We want to find that second crossing point, and if we move everything to one side, in this case I cooked it up so we can factor this. You might have to use a different solving technique, but this becomes x minus 2 times x plus 1, and then you get the x minus 2 equals 0, giving you the x equals 2, so that's that second place. And we also get, just to finish this out, the x equals -1, so that was the one on the left there. So right here, the other place it crosses at 2. Both of them will give you a result of 4. So that means that really all the way over, and this is not going to have the full picture in there, but all the way over to 4, that's our kind of desired region. I'm looking at the area here, and then this area here that gets a little bigger, but hopefully you're getting the sense here. And the most important thing to see in this picture is that at 2, that intersection point, we actually have a switch in which functions are bigger, which function is bigger. So what we're going to do then to set this up is we're going to have the integral from -1 to 2, where the x plus 2 is taller, it's the higher y values, then subtract away the x squared dx. And then we're going to add to that from 2 to 4, that ending point that we're desiring. And from 2 to 4, you can see the x squared is actually producing higher y values. So we'll have x squared minus this x plus 2 dx. And then you have 2 separate integrals you got to work out to get to the final answer. And after you've worked that out, and I did a lot of this by hand, obviously, you end up with 79/6. So I hope that video helps with the concept of finding the area between two curves, and thank you for watching.